Imagine waking up one morning on the 120th thousandth floor of your apartment. You look out the window and see Earth curving beneath you, with clouds floating far, far below. You're not on a plane or a space station, you're in a skyscraper. A skyscraper so tall that its top literally reaches low Earth orbit. Okay? How would that even work? Let's start with the basics. The Kármán line, the widely accepted edge of space, sits about 100 kilometers, or 62 miles, above the Earth's surface. So if we wanted to build a skyscraper that touches the edge of space, it would need to be at least 100 kilometers tall. For comparison, the current tallest building in the world, the Burj Khalifa, is about 830 meters. That means our space skyscraper would be over 120 times taller than the Burj. That's not a skyscraper anymore. That's a vertical continent. First problem, materials. Modern buildings use steel and concrete, but neither of those can support their own weight stretched 100 kilometers into the sky. They'd collapse under gravity like a wet noodle. We'd need some kind of next-level material, something light, strong, and almost mythical. Scientists often point to carbon nanotubes or graphene, which have incredible strength-to-weight ratios. But we don't yet have the technology to mass-produce them, on the scale of, say, a building the height of the stratosphere. Let's say, though, that we magically solve the materials problem. Congratulations, you're the proud owner of a space pillar. Now comes issue number 2, gravity and pressure. Down near Earth's surface, air pressure is thick and gravity is strong, but as you rise higher, both decrease. At 10 kilometers up, the air is so thin that jumbo jets need pressurized cabins. By the time you reach 50 kilometers, you need a spacesuit. At 100 kilometers, you're basically in space. So your skyscraper has to transition gradually from normal Earth atmosphere to vacuum. It would need to be pressurized like a space station near the top and like a mall near the bottom. Essentially, it's not one building. It's several stacked environments, each designed for a different layer of the atmosphere. And speaking of stacking, elevators. Nobody wants to climb 100,000 flights of stairs, but even a super high-speed elevator that goes 500 kilometers per hour would take over 12 minutes to reach orbit, and that's without stops or delays. Also, the cable needed to pull an elevator that high, it would weigh more than the rest of the building, so we'd need some kind of maglev bullet elevator, powered by superconductors and traveling through vacuum tubes. Or teleportation. Yeah, that might be easier. Now let's talk weather. Our building has to survive hurricanes, lightning strikes, jet stream winds, and temperature swings from minus 90 degrees Celsius to plus 30 degrees Celsius. It would be a miracle of engineering just to keep it standing without it snapping like a spaghetti noodle. And if an earthquake hits, well, let's just hope it doesn't. Even if we manage to build this thing and keep it from falling over, orbital mechanics throw in another problem. Orbit means free fall. To orbit Earth, you're not just high up. You're moving sideways really fast, about 28,000 kilometers per hour. A building can't do that. If the top of your building is in orbit, then it's not standing still. It's flying sideways around the Earth, which means it would rip itself apart from the Earth's surface unless it's somehow moving with the same speed, which, spoiler alert, it can't. So technically a building can touch space, but it can't enter orbit and remain attached to the ground. That's just not how physics works. But what if we adjust our expectations? What if instead of building into orbit, we build toward orbit? Maybe a tall tower that launches small rockets or cargo from a high altitude, or a platform that supports a space elevator anchored from geostationary orbit and dropping a tether down to Earth. That idea is still science fiction, but at least it's physically possible, eventually. In the end, building a skyscraper to orbit sounds cool, but it's one of those ideas that makes more sense as a science experiment or a sci-fi setting than as an actual construction project. The amount of money, energy, materials, and engineering required would be so extreme that you'd be better off just building more rockets. Or, better yet, figuring out warp drive. Still, it's fun to imagine. A coffee shop on the 80th thousandth floor, a gym with views of the stars, a penthouse in space with Earth as your backyard. Just don't forget your elevator pass. It's going to be a long ride down.